Welcome to Intermediate Algebra. In this section we're talking about the algebra of functions, and in order to go through this material I'm going to use some notes that were originally adapted for one of Blitzer's college algebra books, but Julie Miller in her intermediate algebra books has covered this material. Depending on what edition of the book you're using, it's either, I think it's chapter 2 section 8 maybe, or it was 3.4, but now it's in chapter 8 section 1. So just be careful that you are using this material or reviewing this at the correct time. And to start our conversation about the algebra of functions, let's just have a look at this kind of collection of information. Adding, subtracting, multiplying, and dividing functions, f and g. And before I forget, I want to point out, just in case you're printing these notes, down here, sometimes when you convert between file formats, not everything transfers. The first circle that I made should be an equal sign, and the second circle that I made should be a does not equal sign. So make sure you fill both of those in, again, so that it's an equal sign here and a does not equals there. And these are all quite straightforward. This is just different notation that allows us to add two functions together, subtract the functions, multiply the functions, and sometimes a little dot like this is going to appear in here with the f and the g. Sometimes yes, sometimes no. And then for the quotient is where we're dividing functions. And just remember that your denominator, whatever function that is, we want to make sure that it does not equal 0, otherwise we have a division by 0, and that we want to avoid. In example 3 here, we see a request for the sum, difference, product, and quotient of these two functions. These are not very exciting because there's not a lot of additional steps that happen. Just realize that we can indeed build these using the algebra of functions. So let's just quickly move through these. F plus g could also be written as f plus g of x. And all that means is we're going to take the f of x function, then add it to the g of x function, and that is x minus 6 plus 5x squared. I wouldn't typically list this or type this in as a final answer. It's acceptable, it's equivalent to the right answer, but in a multiple choice scenario, I wouldn't be surprised if you saw these terms rearranged so that they were in decreasing order of exponent. So now you see the squared term first, and the x to the first power term is coming after that, and then the constant value is coming last. The difference of these two functions, f minus g, is also not very exciting. I'm bored by these already. Because really what we're doing is we're writing down these function names, excuse me, and then replacing them with what they are. So f of x is the x minus 6 minus the g of x is 5x squared. I put the 5x squared in parentheses because if this were anything that had more than one term, we would need to distribute this minus sign to the inside of those parentheses. But as it is, there's only one term in here, so not a lot of distributing that needs to be done. I would, again, write these in a different order. I would put that minus 5x squared first, and then the positive x to the first power, and lastly the minus 6. When we find the product of these two functions, f times g, we will be doing exactly that. We're going to take our f of x function, and I will be putting it in parentheses, and we'll multiply it by g of x. So let's do that. In our first set of parentheses is the x minus 6. Second set of parentheses is the 5x squared. And when we find this product, you can indeed distribute multiplication from the right. Don't hesitate to do that. The 5x squared is going to multiply into the 6, or negative 6, and into the x, leaving us with 5x to the third power minus 30x squared. Normally we distribute in from the left, but it is allowed in this algebra to distribute from the right. Finally, the quotient, f divided by g. It's as simple as that. It's a fraction where the numerator gets replaced by whatever f of x is, in this case x minus 6, and the denominator is the 5x squared. Be aware that you cannot simplify this statement. You could simplify it if you wrote it as x over 5x squared minus 6 over 5x squared. If you want to write it like that, or if it's appropriate for some reason to do that, you may. And at that point, you could reduce by a factor of x here and get 1 over 5x minus 6 over 5x squared. But I would say that this is so much more condensed and tidy that I wouldn't be surprised if you see it left like that. But realize that if for some reason a textbook or an exam wanted to torture you a little bit and kind of drag the problem out, they could present this as what they want or how they want your final answer expressed. So that's the distributive property of division. Took us from here to here, and then simplification took us from here over to here. And those are your 4 basic properties for the algebra of functions. The next property is considerably more unique, where we start building composite functions. Composite functions are where instead of taking a number like 2 and putting it into a function, or taking a variable like m and putting it into a function, instead we're going to take an expression like x squared plus 2x and put it into our function. And this unusual stuff that we're going to plug into our function f is some other function, g of x, which means that what I've just written here is f of g of x. So we're putting a function into another function. This is what you're seeing right here. And another way to denote this is using this notation. Those 2 notations are written for you here. The one on the left is often referred to as fog notation because it looks kind of like it says, well, like it says fog. And it looks like fog because this is an open circle right here. If it were multiplication, that little circle would be colored in or it wouldn't be there at all. But if it's an open circle, you should assume that it is function composition. Fog notation is not the notation that I prefer. Anytime I see fog notation, I then immediately convert it over and I use this notation on the right. It's just more similar to all of the other ways that we've worked with functions. Instead of plugging in a number or a variable, now I'm plugging in a whole function. So I prefer to continue using this notation. So in my notes, you'll see me switching over to that every time. So let's build a composite function. Here we're being given a couple of functions, and the first thing we're asked is to build f of g of x. And I'll make the switch to write it as f of g of x in this way, which means that into my function f, I'm plugging in not a number, not just a variable, but a whole expression. This is now f of 2x squared minus 9. Since this says f of 2x squared minus 9, this no longer says just an x. It says 2x squared minus 9, which means I have to change this x also into a 2x squared minus 9. So let's do that. It no longer says 7 times x, it says 7 times 2x squared minus 9. We do still want to bring this plus 1 with us. That's the most challenging part of the process for you, probably. From here, all we have to do is distribute and combine like terms. But make sure, go back, watch this again if you need to, and make sure that you understand how we got to this point. From here, I'm going to distribute, dist for distribute, so that equals 14x squared minus 63. The plus 1 is still there, and then we will combine like terms, CLT. And we get 14x squared minus 62. Looks good, nice. Part C then asks us to evaluate f of g of 2. In order to do that, all we have to do is take this 2 and plug it in for x. So we have 14 times 2 squared minus 62. I will leave you to do the arithmetic on that. In part B, we're building the function inside out. This time we're going to build g of f of x. That's g of f of x, which means g is the outer function, f of x is the inner function. And what are we replacing this time? Inside of my g function is now an f of x. Over here, I've changed this x to an f of x, which means we're going to change this to an f of x. What is f of x? It's the 7x plus 1. So that's our new input value, which means we're going to do 2 times, not x squared, it's going to be 2 times 7 plus 1, 7x plus 1 squared. And then do bring that minus 9 with you. So again, this is all about simply changing the input value from an x to something else. Whether you're changing it to a number or another variable or a function or an expression, the process works the exact same way. So don't let it intimidate you just because it looks a little bit different. We're doing all the same stuff. All the same processes. From here, the next thing we need to do is FOIL this, 7x plus 1 times 7x plus 1. Some of you don't need to write it out, you can do it in your head, that's great. If you're taking a test, you might want to write it out anyway. That should cause you to slow down a little bit and hopefully decrease the chances of you making a mistake. So I did my foiling. Here's the F-O-I, that's not an I, I-L, and then don't forget to bring that minus 9 with you. So we've done our foiling. We're going to combine like terms here. The 7x plus 7x is going to become a 14x, and we're going to distribute multiplication by 2 to all of the terms inside of our parentheses. So let's do that. Let's combine like terms and distribute, dist. That gives us 98x squared. 14 times 2 is positive 28x. We have the plus 2 and we have the minus 9. So we'll combine like terms one more time, just these constant values here, and we will be done. 98x squared plus 28x minus 7. And you'll notice here that g of f of x does not equal f of g of x. And in fact, it's very uncommon that they will. And I'm pretty sure under all circumstances when you're working with real numbers, if f of x equals if f of g of x equals g of f of x, they'll both end up equaling x. And that happens when your two functions are inverse functions, like squaring and square rooting. They kind of cancel each other out, leaving you just with your input value. This author highlighted that fact for us here, that f of g of x is not the same thing as g of f of x. Excuse me, sometimes it is, but usually it's not. And then we need to talk about domain. When you look at the domain of a composite function like f of g of x, you need to make sure of two things. You need to make sure that you satisfy the domain of the inner function. So if we're looking at f of g of x, then g is the inner function. We need to make sure that we keep its domain happy. And then we will build f of g of x, we'll build the composite function, and then we'll have a look at its domain. And here's an example problem for us to try doing that. The domain of the inner function which is, in this case, g of x, is, have a look at g of x here. This is a rational function, the variable's in the denominator, and when the variable's in the denominator, we want to make sure of one thing in particular. We want to make sure that we don't accidentally cause division by 0. An x value of 0 would obviously cause division by 0 here in g of x. So we're going to just put ourselves a little note that x is not allowed to equal 0. We're sort of building a list of x values that we're not allowed to use. And then at the very end of this process, when we state our domain, we'll convert it and deliver a list of x values that we are allowed to use, because that is the more typical understanding of what a domain is. It's a list of x values that you are allowed to put into your function. Now that we have a note about the domain of our inner function, let's start building our composite function. We're plugging g into f, which means that these x's in our f function need to be replaced by g of x. So we have g of x over g of x plus 5. Then we can take it one step further and replace our g of x's with what g of x actually is, which is 6 over x. So our numerator becomes its own fraction, and in the denominator we have a fraction plus a number. Now, it's pretty clear, I think, that you still don't want to plug in an x value of 0, but we now have more denominators than we did before. I like to refer to this as my big numerator and this as my big denominator. And in my big denominator, where we have this 6x plus 5, I'm going to go ahead and try to add those together by creating a common denominator down there. So I'm going to leave my 6 over x as it is in the big numerator, and in my big denominator I'm going to write this as 6 over x plus 5 over 1 times x over x. And that's going to help me create a common denominator in my big denominator. Big numerator stays the same, and in the big denominator I now have a denominator of x here, and 1 times x makes a denominator of x there, which means I can now add these numerators of 6 and 5x. So I will write my big denominator as 1 fraction 6 plus 5x all over x. Clearly, I still do not want to plug in an x value of 0. However, now that we have a fraction divided by a fraction, we can use keep, change, flip. Remember that division is the same thing as multiplying by the reciprocal. So here's the 6x from the numerator, and instead of dividing it by the big denominator, I'm going to multiply it by the reciprocal of the big denominator. In other words, I will multiply it by x over 6 plus 5x. That kind of ran together. 6 plus 5x. There we go. And in fact, these x's are going to cancel right here, which leaves us with, maybe let's move back to, let's come over to here, and I'm going to write this as 6 over 6 plus 5x. Now, all of a sudden, this thing has taken on a different shape. Now my fraction is 6 over 6 plus 5x. That's a totally different denominator. And at this point, it's very clear, to me anyway, and hopefully it's becoming more clear to you, that we need to reevaluate our domain. A value of 0 plugged into this denominator is not going to cause a problem. But let's make sure that 6 plus 5x, let's make sure it never ends up equaling 0. To do that, I think I will subtract 6 from both sides. So we see that 5x does not want to equal negative 6. And then if we divide both sides by 5, we see that x does not want to equal negative 6/5. So here's one restriction on our domain. Actually, that's the second restriction on our domain. The first restriction said that we wanted for x to not equal 0. So let's look at the question again. Find g of f of x. Sorry, I don't know why I read that inside out. Find f of g of x. Right. There it is. See where it says that? Find f of g of x. We did that. That was here. So that was the first part of our answer. And the second part of our answer is going to be stating the domain, which is going to be all real numbers except for 0 and negative 6/5. And I'm going to put that on a number line, I think. Let's use, let's stay with blue. On a number line, I would shade the entire number line except at negative 6/5 and at 0. I would have an open circle here and an open circle here, and I would shade everything to the left of there and everything between them and everything to the right of 0. Graphically, that's an acceptable way to represent your domain. But let's write this up using interval notation. In interval notation, I examine my shading from left to right on my number line. The shading goes all the way down to negative infinity, comes up to negative 6/5. We will exclude negative 6/5 with a parenthesis or an open bracket, or that's the union symbol, or we could choose x values starting at negative 6/5, but excluding it again with another open bracket. That shading goes up to 0, which we will exclude, or we could choose x values starting at 0 and going all the way up to positive infinity. Notice that those open brackets or parentheses in interval notation are telling us that negative 6/5 and 0 are being excluded from the domain. My guess is that is how you're going to be presenting your final answer for your domain of this composite function. There was a lot of arithmetic involved in this, so don't let that throw you. We went through, we took everything step by step, and if you were going to make a flashcard as part of a review process for how to find the domain of a composite function, I think it was only like a 3-step process. Make a note about the domain of the inner function, build the composite function, and then evaluate the domain of the composite function. 3 steps. Amazing that it took us that long. Decomposing functions is effectively what we just did, but in reverse. And what you want to look out for, and this is going to be great because we've just been using this language so much, is you want to look at a given function that you're being asked to decompose and ask yourself, is there an inner function and an outer function? If there is, if you can identify them, then you're in pretty good shape. I see a couple of things happening here. I see that there is a 5x squared plus 3, and the other thing that I see is that there's a square root. Would you say that the 5x squared plus 3 is inside the square rooting process or outside of it? Another way to ask would be, is the square rooting process happening inside the squaring of the x value and the multiplying of it by 5 and the adding 3 to the result? I don't think so. I think if you plugged an x value into this h function, you would probably do all that 5x squared plus 3 stuff first. And that's what indicates to me, at least in this problem, that that's my inner function. So I'm going to say that 5x squared plus 3 is the inner function, square rooting is the outer function, here is h, and g is the inner function, so this is the 5x squared plus 3. Which means that the outer function is doing the square rooting, so f of x only has one job, and that's taking a square root. Let's look at our multiple choice options. Are there only 2? There are only 2. I love it. Because it's either inner outer or outer inner. And we can see that the g of x function is being listed here as the inner function, 5x squared plus 3. And this is how we denote the task performed by the outer function, in this case f of x. All it's doing is square rooting. It's square rooting whatever you give it as an input. In this case, we gave it an input value of g of x, which is a little more complicated than just plugging in a 2, but that's all right. The square root function can handle it. I hope that this gives you some valuable illustrations of composite functions in particular, both from the perspective of building them and deconstructing them. I think that as you build more composite functions, you'll get more comfortable with the idea of decomposing them or deconstructing them and breaking them up into 2 separate functions. And you can always check your work on a question that asks you to decompose a function into 2 functions like the one that we just did. All you have to do is build f of g of x from scratch and see if you get, in this case, the h of x function again. Nice that there's an opportunity for you to be able to check your own work there. All right. If I haven't misinterpreted any more of the ways that our chapters and section numbers are laid out, this was the last video in what I'm calling Chapter 2, and I look forward to seeing you in Chapter 3. Thanks so much.